Hello all. Let us continue with the next subtopic of chapter 3, that is 3.5, which is wherein we have to study acid and base catalyzed hydrolysis of esters and amide. Now this particular topic is the subtopic is there in this chapter because it is also a type of nucleophilic substitution reaction of carbonyl compounds. Just carefully understand that the name of the subtopic is acid and base catalyzed hydrolysis of esters and amide. So in this subtopic we are going to learn how to hydrolyze esters and amides. So the brief outline of the reaction that we are going to learn, let us look at it. Esterification and amide formation are similar reactions, so they work on the similar mechanism. If you want to make esters, you will have to react carboxylic acids with alcohols, and if you want to make amides, you will have to react carboxylic acid with amines. Now if you just look at the reactants, the carboxylic acid that you have got over here is the carbonyl compound, as this is in the chapter named nucleophilic substitution in carbonyl compound. So the carbonyl compound here is the carboxylic acid, and as you know, alcohols and amines are nucleophiles, are neutral nucleophiles, so weak nucleophiles. So when you take carboxylic acid and you react it with alcohol, you get esters, and if you change the nucleophile to amines, you get amides. Now even though your syllabus has got hydrolysis of esters and amides, we will also learn how to make esters and amides, because both these reactions are reversible in nature. If you take carboxylic acid and you react with alcohol, you get ester. Now hydrolysis of ester will be exactly the opposite of how the ester is formed. So we will learn both the reaction: formation of ester, hydrolysis of ester; formation of amides, hydrolysis of amides. As I told you, alcohols and amines are acting as nucleophiles over here. They are weak nucleophiles. So just recollect that I told you, if the nucleophiles that are used in nucleophilic substitution reaction are weak nucleophiles, then the reaction is going to be catalyzed. Now how the reaction is catalyzed we have seen in earlier lectures. Like your nucleophile is a weak nucleophile, so you want your electrophile to be strong, and when I say the electrophile has to be strong, I am talking about the carbonyl carbon. Now that has to be more positive. If you want to make the carbonyl carbon more positive, you will have to protonate the carbonyl oxygen. When you protonate the carbonyl oxygen, the oxygen carries positive charge, because of which it starts withdrawing more electron from the carbonyl carbon, and the carbonyl carbon becomes more electrophilic. So you will remember the catalyst point of view only if you remember that the nucleophiles used over here are weak nucleophiles. So therefore the reaction with carboxylic acid for alcohol and amines will be acid catalyzed. Okay, this is very important point, that the reaction is going to be acid catalyzed. It cannot be base catalyzed. Now this is very important aspect that we'll be discussing in the upcoming slides, that why formation of ester or amides is not base catalyzed, why it is only acid catalyzed. And if you see the next point where it says that hydrolysis reaction is acid as well as base catalyzed. So just to summarize over here, I told you that in this subtopic we are going to learn two reactions. One is formation of ester or amide, and the second one is hydrolysis of ester or amide. And you have to keep in mind that formation of ester or amide is going to be only acid catalyzed. It cannot be base catalyzed. But the hydrolysis reaction can be both acid and base catalyzed. Now little idea I have already given you that why the reaction can be acid catalyzed, because I told you that the nucleophiles that you are using are weak nucleophiles, so you need to increase the electrophilicity. And since the reaction is reversible in nature, if the formation is acid catalyzed, the hydrolysis also can be acid catalyzed. But the formation can never be base catalyzed, but the hydrolysis can be base catalyzed. So we will see mechanism of all of these. If you refer to the university question paper, question on this is asked in all the papers. Either they are asking the mechanism of hydrolysis, or they are asking this question, that if the formation is only acid catalyzed, why the hydrolysis is both acid as well as base catalyzed. So you have to keep this in mind while studying this subtopic. Let us move to the next slide. So I am showing you a mechanism over here. Remember, this is just to explain you the arrows which are used over here. The reaction arrows are not proper. Actually, this is a reversible reaction, so the reversible arrow should be used. But this is just to explain you the mechanism of what is happening. So as I told you that it is a reaction between carboxylic acid and alcohol. So this is the alcohol and this is the carboxylic acid. As I told you that the alcohols are weak nucleophiles because they are neutral species. The electrophilicity of the carbonyl carbon has to be increased. Electrophilicity of this carbon has to be increased. So that can be increased by using acid catalyst. So as soon as the acid is put, the lone pair on oxygen is donated to H and the positive charge shifts on oxygen. So if you see this particular structure now, the carbonyl oxygen is protonated. So it has become positive. So it starts withdrawing electron from this carbonyl carbon and this becomes more electrophilic. So as soon as it becomes more electrophilic, it attracts the nucleophile. So a bond is formed between carbonyl carbon and the oxygen, which is carrying a lone pair. And this pair shifts on oxygen to neutralize the positive charge. So this is the tetrahedral intermediate formed. As I told you, all the nucleophilic substitution and addition reactions will show you a tetrahedral intermediate. So this is the tetrahedral intermediate form. So now you will evaluate if this is stable. So we say that it is not stable. The instability of this tetrahedral intermediate is because of 3 heteroatoms that are attached to the carbon. So all 3 are withdrawing. So it will not be stable till some group from here leaves. Now if you evaluate over here the stability, or I mean from that perspective, that which group will leave. So out of these 3, which is a good leaving group? You know, the good leaving group is that group which is unstable when it is part of the tetrahedral intermediate, and when it leaves it should become stable. So as far as this structure is concerned, this ROH is unstable over here because of the positive charge on oxygen. Therefore this should become a good leaving group and the reaction should go back. If this leaves, it will go back. But what happens over here is, because of this positive charge on oxygen, this hydrogen becomes more acidic, very highly acidic. So this H migrates to that particular place where there is electron available. So the neutral alcohol that you have in the reaction mixture attracts this H, and this becomes OR. So you can see now it has become OR and the H is lost. Now if you evaluate, the instability is still there. 3 oxygens to single carbon is unstable. Now what happens is, when this takes the hydrogen, this becomes unstable and then it starts donating that hydrogen. So this hydrogen being present near oxygen, which is little bit hindered. See, this is sterically hindered. This oxygen is sterically hindered. So it always prefers to move to less hindered oxygen. So compared to ROH, this OH is less hindered. So it will move to this O. Rather than going through all these steps, we can simply say that you have got RO here and you have got OH here, and this H, because it is now more hindered here, so it moves to this OH or this OH because they are similar, no? So let us say that this H moves to some OH, and you can say that you get directly this. So you can directly draw an arrow from here to here, from here to here. So you say that okay, the H moved from here to this OH. Now this has become a good leaving group. As you know, OH is not a good leaving group, but HOH positive, HOH plus is a good leaving group. So that goes out. See, water has been lost from here, and when this leaves, this carbon becomes positive. this carbon becomes positive. When this group leaves with the electron pair, you can see the curved arrow coming on this oxygen, so this leaves and this carbon becomes positive. So as soon as this carbon becomes positive, the lone pair from this oxygen shifts over here. See, it shifts over here and forms a double bond. Okay, and now this can be resonance stabilized, like when this moves, it forms a double bond, this comes back over here and this moves and forms a double bond. So you get these two structures. So this O plus over here. Now this O plus is an unstable situation, and as you know, the migratory aptitude H has got a good migratory aptitude than R, so this is comparatively more stable, this O plus. So what happens is this H is lost from over here, because O is plus, so it will take this electron pair on itself and this H will be lost. So H is consumed over here and you see the H is lost over here. So the catalyst, you can say, is regenerated and you get an ester over here. So this is the mechanism. It will become more clear in the next slide. As I move to this slide, I was telling you that ester formation and ester hydrolysis is a reversible reaction. So if you note over here, now this is a very simple way of writing the mechanism, and you may write like this also. This is the best mechanism that I have seen. So you have got ester over here, and as I told you, it has to be converted into more electrophilic carbon. It undergoes protonation. As soon as it undergoes protonation, this carbon becomes more electrophilic and it reacts with the nucleophile. So right now we are seeing the hydrolysis reaction. Okay, this is the hydrolysis reaction. So you've got an ester over here and proton is there. So this oxygen undergoes protonation. This becomes more electrophilic, and as soon as it becomes more electrophilic, water, being a nucleophile, attacks on this electrophilic carbon and you get this. Now this is unstable, oxygen with a positive charge, so this H migrates to OR and you get ROH, and this positive charge makes it a good leaving group. This becomes a good leaving group, so it leaves. As soon as it leaves, this carbon becomes positive and it takes the electron pair from one of the oxygens, and that oxygen becomes positive. And then the H from here is lost, because H is taken over here, it is taken, so it has to be lost. So when it is lost, you get the carboxylic acid. This is the simple way of writing the hydrolysis mechanism. Now if you see over here, you have written this over here when the reaction moves from here to here. If you just write this below the arrow, you are talking about this reaction, means this forming this. So if you know the esterification mechanism, in the opposite direction it will become hydrolysis mechanism. So I'll start for esterification from here. So you've got carboxylic acid here, and it will be undergoing protonation. So plus here, so you've written minus here, so it will come up and become plus. So this becomes protonated, then the nucleophile attacks over here, so it was lost over here. See, it is lost over here, so here it is getting added for the reaction to move in the forward direction. Okay, and then when this is added over here, there is a positive charge, so H migrates to this one, you get this, then water is lost, you get this, and then H is lost. So here H is added, here H is lost, here water is added, here water is lost, here alcohol is lost, so here alcohol is added, and here water H plus is lost, so here H plus is added. So a single mechanism, if you remember, you can write the hydrolysis also. Only you have to shift the position and the charges. So here you are writing suppose plus H plus, so you'll write minus H plus, like that. Now base catalyzed esterification or hydrolysis. So I told you that esterification cannot be base catalyzed. So here what I want to tell you, this is very important point, that why esterification cannot be base catalyzed. So just recollect that the esters are made from carboxylic acids and alcohols. Now if you put little base in this, base in carboxylic acid and alcohol mixture, what this base will do is it will react with the carboxylic acid as if you are reacting acid and base forming salt and water. All of you know that acid and base react with each other to form salt and water. So if you take carboxylic acid and you add alcohol and you try to make ester by putting a base, the base will abstract the proton from the carboxylic acid, the acidic proton of the carboxylic acid, and what you will get is the carboxylate ion. Now when you have got carboxylate ion, because of the negative charge on oxygen, okay, what I am trying to tell you is this is the carboxylate ion. If you react carboxylic acid with a base, you will get this. Now when you get this, the carbon over here becomes very poor electrophile, because this is electron rich. So this is very stable, this is resonance stabilized. So the electrophilicity is lost, and that is why a very weak electrophile and there is already a weak nucleophile, they cannot react to form ester. Okay, so I just repeat once again, when you react carboxylic acid with alcohol using base as a catalyst, base removes the proton from the carboxylic acid and makes it a carboxylate, and the carboxylates are not good enough electrophile to react with the weak nucleophile. So therefore esterification cannot happen. Whereas if you talk about the hydrolysis, you have got the ester functional group over here now, and you have got this carbon which is electrophilic, no doubt, and you have got a very strong nucleophile over here. So even if the electrophilicity of this carbon is less, it will still react with the base, and this will attack on this particular carbon, and you will get this tetrahedral intermediate. Now what is happening in this tetrahedral intermediate is there is lot of instability. You have got 3 oxygens over here, so one group has to leave, and you know that OR group is a good leaving group. Okay, we have discussed about the leaving group capabilities and the pKAH values, and I told you that OR group is a very good leaving group. So it immediately leaves, and the pair of electron from this O minus shifts over here. So when this leaves out, and you get the carboxylic acid and OCH3 minus. Now OCH3 minus is a base, so it will take this acidic proton, and you will get the carboxylate ion with the alcohol. So this is a very simple mechanism for hydrolysis of esters by base catalysis. Now we come to amide formation. Now the mechanism of amide formation is exactly similar to mechanism of ester formation. The only difference is, in this case the nucleophile is amine, over there it was alcohol. That is the only difference. So you see it is moving on the same lines. O gets protonated, then the nucleophile attacks. When the nucleophile attacks, there is a positive charge on nitrogen, so the H from here will migrate to one of the OH. See, it migrates to this OH, and you get OH2, which becomes a good leaving group. So this group leaves, this carbon becomes positive. When this carbon becomes positive, it takes the electron from the atoms which are having lone pairs. So it takes electron from this oxygen, and this H then leaves because this will become positive, and you get the amide. It is exactly similar mechanism, only in place of oxygen you have got nitrogen. So this is acid catalyzed amide formation. Now if you talk about acid catalyzed amide hydrolysis, it will move in the similar manner. If you remember, in the last step there is loss of proton, this proton is lost. So here in the first step the protonation will happen. So when the protonation happens, this becomes OH with a positive charge here. Okay, and that positive charge can come on nitrogen also. If you just see here, this nitrogen is positive, and then this takes the pair, and this oxygen gives the lone pair, so this becomes positive. So they are becoming positive alternately because resonance stabilized. So like that, this oxygen becomes positive. Okay, now when this oxygen becomes positive, it starts pulling electron from this carbon, and this becomes electrophilic carbon. So water as a nucleophile will attack on this carbon, and you will get this. So when water attacks over here, the oxygen becomes positive, so it loses one hydrogen from here to this, and you get this particular structure. Okay, and then this becomes a good leaving group, it goes out, and then one of the oxygen will get a positive charge, so it will give out the H, and it will become this OH gives H, and it becomes carboxylic acid and the amine derivative. So if you just move in this direction, I mean you move from here, you will find the acid catalyzed amide formation. So it is a reversible reaction. See, this is the acidic proton which will protonate OH, and then the nucleophile will attack, and after the nucleophile attacks, the H from here migrates to this OH, see here, and then that becomes a leaving group, so H2O is lost, and then the H from here lost, and you get the amide. So it is a reversible mechanism. Base catalyzed amide formation. Now as I told you that the ester formation cannot be base catalyzed, for the reason that the base catalyst will take the acidic proton from the carboxylic acid and it will reduce its electrophilicity. Same applies to the base catalyzed amide formation. Amides cannot be formed by base catalyzed mechanism for the same reason, but they can be hydrolyzed by base catalyzed mechanism. So if you see this mechanism, you have got amide over here because of this carbonyl group and then electronegative nitrogen. This is more electrophilic, so the nucleophile base that you have used attacks on this electrophilic carbon and you get this tetrahedral intermediate. Now this tetrahedral intermediate is unstable, so it will undergo protonation. See, this water which you have got protonates this amine and it becomes NHR2 plus. So this becomes a good leaving group and it goes out, and this pair shifts over here and you get a carboxylic acid. So like you have got base catalyzed hydrolysis of esters, very simple mechanism. You have got base catalyzed amide hydrolysis also, very small mechanism and very easy to understand also. So just to summarize the subtopic, esters and amides can be synthesized from carboxylic acids by reacting carboxylic acids with alcohols and amines using only acid catalysts, whereas esters and amides can be hydrolyzed to carboxylic acid and alcohol or carboxylic acid and amine using acid or base catalysts. These reactions are nucleophilic substitution reaction. Thank you so much. Happy learning.